Hello and welcome. If you're wondering what those boxes are back there, don't ask. So in example 5, we're looking at the integral of negative 2x plus 4 all over x squared plus 1 times x minus 1 squared. So here we've got an irreducible quadratic. That's the x squared minus 1, x squared plus 1. That can't be broken down further. And then we've got x minus 1 quantity squared. So that's a repeated linear factor. So it's going to be a fairly beefy partial fraction problem. It's always nice. So the first thing we're going to do is write the form of the partial fraction expansion. Break it down by writing the form. And as we mentioned in a couple parts ago, the irreducible quadratic gets its own fraction. So it gets to be on the bottom of its own fraction. And above an irreducible quadratic is going to be something like ax plus b. So it'll be something times x plus something. Whatever letters you're at, you fill in the somethings. Now for the repeated linear factor, we're going to have as many little fractions as the exponent. So in this case, we've got an exponent of 2. So we're going to write two little fractions. Above each of those is going to be a single letter because we're coming from a linear factor. This is just x minus 1. So that's a linear factor. So above each of these fractions will just be a single letter. Now we're already up to c, so we'll write c and then d. And then below them are going to be all the powers up to the second power. So if this were x minus 1 to the 5th, we would have x minus 1, then x minus 1 squared, then x minus 1 to the 3rd, then x minus 1 to the 4th, and x minus 1 to the 5th. All right, thankfully we just have x minus 1 squared because that would be a lot of letters on the top. Now, as a first step, we're always going to clear out those fractions. So let's multiply both sides by x squared plus 1 times x minus 1 squared. It's always multiplied by the denominator, the original denominator that you had. So on the left we have 2x plus 4. On the right we have ax plus b. That's not going anywhere because it's on the top of the fraction. Then the x squared plus 1's cancel, and we have x minus 1 squared on the top. Plus the c is not going anywhere, so we have an x squared plus 1 left over, as well as one of the x minus 1's. One of these x minus 1's cancels with one of these, and so we just get one of them left. So then we have plus d times x squared plus 1. Here, both of the x minus 1's cancel. Now, at this point, again, we have a couple of different choices. We can either expand everything out and do it that way, or we can look for x values that we could plug in to get some of the undetermined coefficients. Again, I call that the low-hanging fruit. And if there is any low-hanging fruit, might as well pick it. So let's go ahead and find an x value that we could plug in that would get rid of all of the undetermined coefficients except for one. Do you see which one it is? There's a little bit of a clue. It's 1. X equals 1. We can plug in x equals 1, and on the left side we'll get 2. On the right side, the x minus 1 factor, the terms that have x minus 1 factors, will become 0. And then we'll just have the d term, which is then going to be 1 squared plus 1, which is 2 times d, so 2d. Whoops. So then we get d equals 1. Again, plugging in x values can really help if you can identify which ones get rid of all the undetermined coefficients except for one of them. Okay, now when you go looking for other x values, there aren't really any other x values that get rid of all the undetermined coefficients except for one of them. You could try plugging in x equals 0, which would get rid of a, but it doesn't get rid of b or c, or d for that matter. So we've picked all the low-hanging fruit that we could. So now let's go ahead and start distributing everything out. And we can use the fact that we already know what d equals. D equals 1. So let's start writing what it looks like to distribute this out. I'm going to expand the x minus 1 squared into x squared minus 2x plus 1. Expand out the x squared plus 1 times x minus 1, and we get x cubed minus x squared plus x minus 1. And then here there's nothing really to expand out, but we will say that this part right here now is 1. So d is 1. Now we're going to write out the whole thing again, oops, but expand it out. So make some horizontal space here. And we're going to take the ax plus b, multiply it by x squared plus 2x minus 2x plus 1, doing a big, giant, massive FOIL. So we'll take the ax, multiply it by everything, the b, multiply it by everything, and we'll get ax cubed minus 2ax squared plus ax. Here you've got to be real careful not to make mistakes. Plus bx squared minus 2bx plus b, switching to a slightly skinnier font here. And then the c will distribute, so plus c x cubed minus c x squared plus c x minus c plus, and again, the d is 1. We already know what d is, so we don't have to have that fourth undetermined coefficient in our system of equations down the road. We already know what d is. It's great. So we just have plus x squared plus 1. Now, because this doesn't have any undetermined coefficient attached to it, the x squared plus 1 that is, we can move those two terms to the left. We'll subtract those terms to the left, and we'll get negative x squared minus 2x plus 3 on the left side. On the right side, we'll combine like terms and factor out the variable part of each like term. So for the x cubes, for example, the x cubes, we have 2 of the x cubes. So we'll write a plus c times x cubed. Then we have some x squareds. You can write out those. I've never picked that color, purple. So we'll write out the x squareds. Looks like whoops, not that x squared because these are gone. Let's go ahead and cross those out before we accidentally use them. So then right here we've got plus negative 2a plus b minus c all times x squared. We'll do the same thing for the x's, and here I'm just going to do it by looking at it. We have a minus 2b plus c all times x, and then the constant terms that don't have variables attached to them, which are b minus c. Okay, let me scroll down, give us some room. Now, the coefficients of like terms on each side are going to have to be equal for any value of x, for this to be true for any value of x. And so we're going to have a bunch of things here. We have the a plus c coefficient of x cubed has to match the it has to match the x cubed coefficient on the left, which you don't really see, but you can imagine there's like a 0x cubed here on the left, so it would match that 0 coefficient. So we would have a plus c equals 0. Then we'll look at the coefficients of x squared. We'll match those. So we have negative 2a plus b minus c equals negative 1. Then we'll match the coefficients in front of x. So we get a minus 2b plus c equals negative 2. And then match the coefficients, the constant coefficients. So we get b minus c equals 3. So there's our system of equations. Again, D is solved for already, so we don't have four unknowns in our system of equations, which is great. We do end up having 4 equations, and that's because we had all the way up to x cubed. But here it's an overdetermined system. We have 3 unknowns and 4 equations, so it's kind of overdetermined. All right, so let's go ahead and solve this. We have a couple of freebie equations in our new system. So we have, for instance, a plus c equals 0 is missing the b variable. So that could be an equation that we could use in our smaller 2x2 system. In fact, I'm going to use that one. So I'll write a plus c equals 0. Now all we need is another equation that has a and c in it. And we'll go ahead and get that other equation by taking equation 2 and equation 3 and eliminating the b variable from those 2 equations. The way we can do that is by taking the second equation and multiplying it by 2, and then adding it to the third equation. That's my little notation for doing that step. So take 2 times the second equation plus the third equation. And when we do 2 times negative 2a, we'll get negative 4a, plus a would be negative 3a. The b's will be gone because 2b plus negative 2b is 0. Then the c's will have negative 2c plus c, which is negative c. And then don't forget the right side. 2 times negative 1 is negative 2, plus negative 2 is negative 4. So now we've got a 2x2 system. All we have to do now is eliminate one of those variables, and that's not too bad because we can add the 2 equations and c will be eliminated. So we end up getting, it looks like negative 2a equals negative 4, so a equals 2. Again, we can take that a equals 2, feed it back into either of the 2 equations to get c. Then we can feed a and c into one of the original equations to get b. So just feed them back in, and you'll end up getting b equals 1 and c equals negative 2. So feed those 2 in, and that's what you'll get. All right, so now we have the expansion and we know the undetermined coefficient, so we'll know exactly how everything expands. So we're going to feed the a, b, c, and d back into the original breakdown. And when we do that, it's going to look something like this. So here's the original integral. So we're going to have the integral of 2x plus 1 over x squared plus 1 minus 2 over x minus 1 plus 1 over x minus 1 squared dx. Okay. Now we're going to integrate term by term. This first fraction, the 2x plus 1 over x squared plus 1, that one may look a little bit tricky. How are we going to integrate that one? Well, it turns out that if you take that fraction and you split it up into 2 fractions by this plus on the top here, so do 2x over the bottom plus 1 over the bottom, that's going to make it easier to integrate. So here we'll have 2x over x squared plus 1 plus 1 over x squared plus 1 minus 2 over x minus 1, and then plus 1 over x minus 1 squared dx. Okay, because now what we'll be able to do is to evaluate the first integral or antiderivative, what we can do is a u substitution. We'll let u equal x squared plus 1, and the du is sitting right there. It's 2x dx. So a u substitution on that first part. For the last one, we'll also use a u substitution, but here we're going to let u equal x minus 1. Just like we did in example 3. The other two are just straight up integral antiderivatives. The antiderivative of 1 over x squared plus 1 would be inverse tangent of x. And then the integral of 2 over x minus 1 is just going to be an ln of absolute x minus 1 with a 2 in front. All right, so here we'll write, after you do this substitution, so I'm not writing all the details out here, but after you do the substitution, you're going to end up with a 1 over u, which becomes ln absolute value of u, which is ln absolute value of x squared plus 1. Again, 1 over x squared plus 1 we said was arctangent, so inverse tangent of x. And then we have minus 2 times ln absolute x minus 1. There, technically it's a u substitution for this one as well, but it comes up so often that we go right to the ln. Just be careful that you have to have it just an x minus something or an x plus something for this to work. If you have a 2 in front of the x, you're going to have an extra factor of a half out in front because of the substitution that actually goes on. Now, after you do the substitution for the last term, we'll end up with minus 1 over x minus 1, and we'll put a plus c, and we will be done. So we can box that and celebrate. Yay! All right, thanks for watching, and see you in the next part.